So next up, we're just going to do two examples of integral defined and implicit solutions where this idea of using definite integrals can help us out. So in our first example, we're going to consider trying to solve dy dx equal to e to minus x squared if we have initial condition y of 0 equal to 10. So if we wanted to solve this as a separable equation, we would go ahead and rearrange that we've got dy on one side, no y's to move over, is equal to e to minus x squared dx. And then we would go ahead and try to integrate this. So we've got integral dy is equal to integral e to minus x squared dx. And I could go ahead and solve that for y, but I'm going to run into the problem that I cannot evaluate the integral of e to minus x squared. So that's a problem for me. So I'm going to go ahead and instead try to write this out as definite integrals. So I'm going to say, okay, I'm changing to that u and s, those placeholder variables, but if you wanted to keep this y and x, that would be fine. I can't evaluate the integral, but I can go ahead and at least show how I would use my initial condition. So I would be solving for going up to y and going up to x, and my initial conditions are that x started at 0 and y started at, y started at 10. So now I have the integral set up with the initial conditions, which is nice. And the left one I can't evaluate. U goes from 10 to y. And the right side I can't, but I would at least get y minus 10 is equal to the integral from 0 to x of e to minus s squared ds. So I have some kind of solution. Y is equal to 10 plus that integral that I don't quite know what to do with. This is called an integral defined function or solution. It has an integral in it, but it's as close as we could get to the answer without solving that integral. And so that's the first example of a place where we can use definite integrals to write down more of a solution than if we didn't use them. And I'm mentioning this because, maybe on an exam, you should be able to evaluate all the integrals, but if a little something went wrong and you end up at an integral you don't know how to solve, a good way around that is to sort of fill in everything you can so that I can at least give you credit for using your initial conditions, even though you kind of backed yourself into a corner where there's an integral that just didn't work out. Another example of when definite integrals will be useful is, actually we don't need definite integrals for that. We'll actually use this one the regular way, that's fine. But next up we're going to talk about implicit solutions. So we've got this big messy differential equation. Given right there. It is a differential equation because we've got a dy dx. There's so many cosines, sines, and exponentials that you might not notice it, but it is there. And we actually can rearrange this with all the y's on one side, all the x's on the other, so it is a separable equation. I'm going to go ahead and do that. So first I'm going to move all the y's to the left. So I want to keep that e to 2y minus y. I want to keep that dy. And then I'm going to move that e to y over. So I'll just divide by e to y right there. And now everything that has y is on the left side. And then I want to move all the x's to the right. So I'll keep this sine 2x right where it is. I'm going to divide by this cosine x. And then move that dx over as well. So it's a separable equation, and we can go ahead and try to solve it. We're going to have to integrate both sides, and I do want to note that when you have something in the denominator, you can divide all the terms in the numerator by it. It's not true opposite though, just be careful. Like if I had one thing on top and two on bottom, I can't split them up. But in this case, I can do e to 2y divided by e to y is just e to y. And y divided by e to y is y e to minus y. It's just a little bit easier for me to see that. And we're going to be integrating both sides. Sorry if there's a jump in the video there. I had to pause real quick. But so we're to the point of trying to evaluate these integrals. And I just want to get this point across. I'm not super worried about your ability to do like trig sub and integration by parts. So I'm just going to tell you this integral. Integrating e to y is just e to y, but then this minus y, e to minus y, you would do integration by parts, get minus y, e to minus y, plus e to minus y. Not a tricky integral, but it just would take more time than I really want to spend on the rest of this video. And then we're going to do this the indefinite integral way, so let's go ahead and put a constant there. And then integrating the right side is a trig identity problem, and we would get minus 2 cosine of x plus a different constant. And next we would be trying to solve for y. Unfortunately, this is quite messy. You've got e to power y and y separate from that. So we can't just apply natural log, or else we would put this y inside a natural log and sort of end up in the same place. Hit pause if you're still copying that down, but I'm going to move to the next slide so I can show you how we'll deal with this. Our problem is that we can't solve for y equal a bunch of stuff. But we can still use our initial conditions. Y of 0 equals 0 to try and get rid of our unknown constants. So we're going to have e to 0 minus 0 times e to 0 plus e to 0 plus that first constant equal to minus 2 cosine of 0 plus that second constant. So e to 0 is 1. Cosine of 0 is also 1. And we'll go ahead and call all our constants just like C1 put together. That's K minus C. If you want to just sort of always have your constants be called C, that's fine with me. Just renaming them C as you go. I'll understand that you're combining them or dividing them. For you all in the notes, I try to be accurate, so that's why I do all the different notation. But if it was just me working through it, you would see 3 different C's that all mean different things. So I don't care if you do that. Anyhow, this does tell me that C1 would be 1 plus 1 is 2, and then I move that 2 over there. So plus 2 is 4. So my solution is e to y minus y e to minus y plus e to minus y is equal to minus 2 cosine of x plus 4. So all I've done is I've plugged in that unknown constant C1. And again, this is a case where I've used my initial conditions, so I've gone further than if I just sort of gave up when I couldn't solve for y. I still haven't solved for y. This is what's called an implicit solution to the initial value problem because it doesn't explicitly solve for y. And it's still a valid way to have a solution. So just bear this in mind if you ever run into a problem where you can't solve for y. And I think that's all I wanted to do for this section. So nice work, everyone. And then I will see you for the next set of videos.